Topic 6.2. We'll start today. We're looking at Newton's law of gravitation, and we'll cover a lot of this today. Notice there's three equations, you guys. F equals g m over r squared, g equals f over m, g equals g times m over r squared. Good stuff. And this is it. This is Newton's law of universal gravitation. F equals g m over r squared. This was an enormous discovery for him, and I want to talk a little bit about the history behind it, and then get into how we can apply it. But that's it. That's his law right there. It's a mathematical equation that describes the force of gravity between any two masses in the universe. So I do want to actually give you a little bit of history behind this. So the first few slides that we're going to talk about, you guys, are not on the IB syllabus anymore. Not something you need to concern yourself with in terms of will you be tested on it. I know that's important for you. Will you see it on a test? The answer will be no. I will tell you when you need to start taking notes. Okay, so let me just backtrack for a little bit. First of all, if you walk outside and you watch the sun over the course of the day, what would you see it do? Go whoop, and where would it rise? In the east, and it would set in the west. Cool. And then if you walked outside at night and watched the stars, what would you see them do? And they would do the same thing. They'd rise in the east and set in the west, and so would the moon. And then if you came back and I said, hey, tell me what you observed and tell me what's going on. Tell me why that motion is happening. Why the sun and the moon and the stars are doing what they're doing. What do you think you would say? Okay? That's the easy answer, and it is the obvious answer, that they are going around us. The Earth feels like it's stationary. Sure looks like the sun goes around us. It looks like the stars go around us. It looks like the moon goes around us. And that is the belief that people had for thousands of years. And it's a system that puts the Earth at the center of the universe and has everything going around the Earth. This is a model of this geocentric system that was given to us by Aristotle, although other people thought of it as well. So it's a pretty good system. It describes what we see pretty darn well. But there's one problem. There's one go. So here we have four of the zodiac constellations. And just so you know, these constellations, if you go outside tonight, you can find them. They look just like this. And they'll look like this again tomorrow and the next night. They've looked like this for thousands of years. They will look like this for thousands of years more, okay? They are pretty consistent year after year after year, and they rise in the east and they set in the west every night. Now, that all is easily explained by putting the Earth at the center and having things go around us, but there were 5 other stars that were different. And people that observed this stuff watched for a long time, and what they noticed is these other stars, they behave differently. And let's imagine one is right there. If I saw it there tonight, it would rise and set with Taurus, just like that. But then tomorrow night, it would have moved a little bit. And then if I watched it over the course of a week or two, I would notice that it would be moving through the background of the constellation Taurus. That would be probably a month or so right there. And if I watched it over the course of a year, it would continue moving through these background stars. And not only that, every once in a while, it would turn around and go backwards. And then it would continue on its forward march through the background stars. Now, these 5 stars were weird. They wandered through the background stars. They were called the wanderers. And the Latin word for wanderer is planet. And so we call them planets today, okay? And there was 5 of them. They called them Mercury, Venus, Mars, Jupiter, and Saturn. Those are the 5 planets you can see without a telescope. And for thousands of years, people could see these things. And so when people started trying to make models of the universe, it was easy to say the Earth was the center and everything was going around us except for these 5 planets because they behaved differently. And that was a problem. Well, turns out there was an ancient Greek scientist, philosopher guy who came up with a better model than this one to explain this weird motion of the planets. His name was Ptolemy. He lived down in Egypt, and this was the model he came up with. The Earth was still at the center. The planets orbited around the Earth, but they didn't just go in circles around the Earth. Instead, they had these smaller circles around the bigger circles. And because they were orbiting in these little circles around the bigger circles, you could essentially, by doing the numbers right and putting in the periods of these 2 different motions, you could cause the planets to look like they go like this as they went around the Earth, right? Which is what we observe. They go forward, and then they go backwards for a little bit, and then they go forward again. And so this Ptolemaic model was a really good model. It made predictions. It was able to explain why the planets wandered the way they did. Great stuff. And it was such a good model that people believed it for about 1,500 years, right? Ptolemaic model lasted for, about 1,500 years. And then in the 1500s, I think it was, might have been the 1600s, this other guy comes along. And he says, you know what, this model's great. It explains everything we see, but boy, is it complicated. And I think there's an easier way to explain our observations. And the easier way to explain our observations is by taking the Earth out of the center of the universe and putting the sun there. If the sun is at the center, and Earth is just one of the planets going around it, and the Earth is spinning, then that will also create what we observe. It makes it look like the sun and the stars and the moon go around us, and that works out great. Who came up with this idea? Nicholas Copernicus. Good. Nicholas Copernicus. Now, he was a smart guy, smart enough to figure this out. This is pretty crazy geometry. But he was also smart enough to know that this was a really dangerous idea, and that if he had published this idea, he probably would have been killed. Okay? So he didn't publish it. He wrote down all his notes. He had his diagrams. He wrote a whole book about how this works, and he didn't share it with anybody. And then as he was dying, he's on his deathbed. He's totally ill. He's on his deathbed. He's like, oh, I'm dying. Pulls his book out and says, here, world, take this. And then he dies, so they couldn't kill him. Awesome, okay? So then Copernicus's idea is out there. Now, today we look back and we're like, wow, that was brilliant. But I want you to recognize that most people saw Copernicus's idea as ridiculousness. Because in order for this model to work, the Earth has to be spinning every 24 hours and going around the sun every year. And if the Earth is spinning every 24 hours, that means you and I are traveling at 700 miles an hour right now towards smuggling. And I don't feel like I'm moving at 700 miles an hour. And if I walk outside, there's not wind blowing past me at 700 miles an hour. So Copernicus was an idiot. There's no way that I'm traveling at 700 miles an hour. If I throw something up in the air, it doesn't go flying off to the side because I'm spinning so fast. Totally crazy. And just like you guys know, if we're going around the Earth every 24 hours, why don't we just go flying off into space, Mr. Copernicus, huh? Why don't we do that, smarty pants? Well, you guys know, since you've studied circular motion, you did this calculation for homework the other day. Hopefully you remember that the centripetal acceleration needed to make you go around is way less than 9.8 meters per second squared. So the gravity pulling on you is totally strong enough to keep you in that circular motion. But back in the day when he first proposed this idea, they didn't understand that as well as we do now. And they thought, if we're spinning, you should be flying off into space. So it was a debated concept, this Copernican model, and not everyone believed in it. Then we go to Denmark. There was this guy in Denmark. He was born of the nobility class, and he could have easily done nothing with his life. But instead, as a young child, he decided he wanted to be an astronomer. Because when he was a kid, they told him there was going to be an eclipse, and he went out to watch the eclipse, and it didn't happen. And he went out the next day, and it didn't happen. And he went out there like 3 days later, and it finally happened. And he's like, God, that is so crazy that like the best scientific minds of our age can't predict things. That's stupid. I'm going to do better. I want to be an astronomer. So he went to the king, and he said, King, I want to be an astronomer. I need an island. And the king said, all right, I'm going to give you an island. And so he was given his island off the coast of Denmark. It was called Ven. The guy's name is Tycho Brahe. And on this island off the coast of Denmark, he built the best astronomical observatory that had ever been made. This is before the invention of the telescope. So essentially, he built these huge devices to measure angles. And for like 20 years, he measured angles of the planets as they moved relative to the stars. He very precisely measured their location. And it was the best data set that had ever been collected. And he sat down to figure out exactly what's going on with the heavens. Is the sun at the center? Is the Earth at the center? What's happening? He came up with a really crazy idea, which no one ever really talks about and you don't really need to know about, but it's just something to see. He was smart enough to know that it was good to keep the Earth at the center. And he put the sun going around the Earth, and he had all the planets going around the sun. So the Earth was still the center of the universe, so the church couldn't kill him, and everything was kind of weird, and it was a very strange model. Okay, that was Tycho Brahe. He ends up, at the end of his life, he gets really ill. He hasn't figured out how the universe works. He's really sad because he's got 20 years worth of data, and he's about to die. We'll take a little side turn here for Galileo. Galileo is about the same time as Tycho, and the main thing that Galileo did, we've talked about Galileo's law of falling bodies, but the main thing he did in this story is he took a telescope and he pointed it at the heavens. This was huge. No one had ever used a telescope to look at the stars before. He saw all sorts of things that started to break down the Aristotelian geocentric model. He saw sunspots. That was crazy because the sun was supposed to be like this perfect sphere that was perfect and didn't have any blemishes. It has these spots on it. He saw mountains on the moon. You guys think about this for a second. Galileo was smart enough. His telescope was about as strong as like a pair of average binoculars today. He aimed that telescope. Imagine taking a pair of binoculars and looking at the moon with it, and looking at the shadows cast by the mountains, and then using some geometry and calculating how tall those mountains were. And that's exactly what Galileo did, and he was actually correct. He was very close with his approximation. So he's a pretty smart guy. This was his biggest discovery, though. He took a telescope, he aimed it at the planet Jupiter, that wandering star, and he noticed that that wandering star had 4 other little stars that seemed to be orbiting around it. He watched them over the course of a couple of weeks, measured their orbits, and the reason this was huge was because it was the first definite piece of evidence that the Earth was not the center of the universe, that there was something else that had objects orbiting around it. And so there was observational evidence that the Earth may not be the center of the universe, and that was huge. It was a big deal. He found out that Venus went through phases. Again, that was much easier to explain if the sun was at the center and the Earth was not. He also noticed that the planets change in their brightness. Again, difficult to explain if we're the center of the universe and they're just going around us. Why would they get brighter and dimmer sometimes? So Galileo gave us a lot of evidence that helped break down the old geocentric model. And he got into a lot of trouble for it. So Galileo's information really helped move forward the idea that the Earth was not the center. But there was this guy that worked with Tycho Brahe. Okay, Tycho Brahe, remember, he was Danish nobility, very wealthy. He collected data for 20 years and couldn't figure out the puzzle. But he had an assistant. His name was Johannes Kepler. He was a German man, mathematician, brilliant mathematician, but incredibly different life than Tycho. Tycho was super wealthy. Kepler was super poor. Kepler never knew his dad. His mom was tried for being a witch. They didn't convince it, so she didn't get killed, but his aunt was burned at the stake for being a witch. He had like 6 or 7 siblings. Half of them died. His mom gave him up to the church to be raised by the priests. I mean, he was really just a tough life. But he was a brilliant mathematician, and he got a job working for Tycho Brahe. And for years, he's like, Tycho, give me the notes. I can figure this out if you can give me the data. And Tycho knew this kid was smart and knew that he could probably figure it out, so he never gave him the data. He'd give him little pieces of it. He'd be like, oh, here's a little bit. Go play with that for a while. And then and Kepler would go play with the moon or whatever and come back. Well, Tycho's dying, right? He's on his deathbed. He's ill, he's dying, and he's just realized that his whole life has been to collecting data, and he couldn't figure out the answer. So he's on his deathbed, and he takes out his notes, and he's like, Kepler, take my notes. Do not let me have lived my life in vain. Go do something great with them. And then he dies. Kepler's like, yeah, I got the notes. And he sits down to work. And he's like trying to figure it out. And he did. He figured out 3 things about planetary motion that are huge. And these are known as Kepler's laws of planetary motion. They are not part of the IB syllabus, but I do want you to start writing these down now because they are important. They are good things. They're called Kepler's laws of planetary motion. Johannes Kepler, his first law of planetary motion, okay, that he recognized with this data was that the planets do go around the Earth, but they don't go around the Earth, around the sun, my bad. They don't go around the sun in circles. Up to this point, everybody thought orbital motion had to be circular motion. And the first thing that Kepler figured out was that it's not. It's elliptical. So his first law says that the paths of the planets are ellipses rather than circles. His second law is known as the equal area law. And he figured out that as a planet or an object orbits the sun in its elliptical orbit, the area that it sweeps out in any given time period will always be equal. What that means to you and me is that when a planet or an object is closer to the sun, it's moving faster, and when it's farther from the sun, it's moving more slowly. That's basically Kepler's second law. The closer the planet, the faster it moves. The farther the planet, the slower it moves in its orbit, okay? And Kepler's third law is a mathematical law, and he recognized that there was a relationship between the period of a planet's orbit and the radius of a planet's orbit. And the relationship is t squared and r cubed. And that ratio of t squared to r cubed will be constant for any planet going around the sun. Now these laws, they're big laws. They're to this day, they're known as Kepler's laws of planetary motion. And the crazy thing about them is he knew that these were true because he had the data that showed that they were true, but he had no idea why they happened. He didn't know why planets move faster when they're closer and slower when they're far away, and he didn't know why there was a relationship between the period of a planet's orbit and the radius of its orbit. But every planet, you pick any planet, and you take how long it takes to go around, and you square that number, and you divide it by how far away it is cubed, and that number, that ratio is the same no matter which planet we're talking about. Mercury, Venus, Earth, Mars, Jupiter, Saturn, Uranus, Neptune, that's the same. It's weird. Now, he didn't know why, but he knew it was true, okay? Those are Kepler's laws. So here's a quick picture that just kind of explains Kepler's second law, the equal area law. Basically, if you look at a planet, again, its orbit, this first law says the orbits are not circular, they're elliptical, they're like ovals. And basically, if you measure the area that a planet sweeps out over a time period, that area will stay constant. So the consequence of this is when a planet is closer, it has to be moving faster in order to do that. And when it's farther away, it has to be moving more slowly to do that. Again, he didn't know why any of this worked, and it took Sir Isaac Newton to tell us why. Okay? Newton basically made a big shift here. At this point, a lot of people thought that what happened on Earth and what happened out in the heavens were separate, and he did not separate them. He said, hey, what works down here has got to work there. And the story goes that he saw an apple fall from a tree, and he thought about gravity pulling that apple down, and he thought, well, that's weird. Now, if gravity's pulling the apple down, shouldn't gravity also be pulling the moon down? And why isn't the moon falling down? And then he started thinking more about it. He said, you know what, wait a minute, the moon's going around the Earth. That's circular motion. And so I know that the apple falls with an acceleration of 9.8. I wonder how fast the moon's accelerating. And he set out to do some math. And he used his math of circular motion and the understanding of this moon going around the sun, and he calculated how fast the moon is accelerating. And it turns out that the moon is accelerating 1/3600th of 9.8. Now, that's significant because it also turns out that the moon is 60 times farther away from the center of the Earth than the apple is. And 60 squared happens to be 3,600. So he started thinking about, well, shoot, if the moon is 60 times farther away and it's accelerating at 1/3600th, then maybe the force of gravity gets weaker the farther away from the Earth you get. And maybe since the moon is 60 times farther away, maybe the Earth pulls on it gravitationally 1/60th squared as much as it does of the moon, of the apple. So this was the beginning of him trying to figure out how gravity works. And he used the moon, he used the apple, took him a long time, and he came up with his law of universal gravitation, okay? So he recognized that the moon's accelerating much more slowly than 9.8, actually 1/3600th of 9.8, and he did that using v squared over r. I think you guys did it too as a homework problem. Wasn't there a homework problem where you had to calculate the centripetal acceleration of the moon? And it was like 0.002 or 0.0027 something? You guys remember that? You did what Galileo did. The apple accelerates at 9.8. The moon accelerates at 2.7 millimeters per second squared. Okay? Okay? What's that? So with this observation of the moon and circular motion in the apple, here's what he came up with. Make sure you have this written down. This is Newton's law of universal gravitation. And here's what it lets you do. It lets you calculate the strength of the force of gravity, how strong gravity is between any two masses anywhere in the universe. Big G is the universal gravitational constant. M is the mass of each of the masses, mass A and mass B. And R is the distance between the centers of the two masses. So what he figured out was that gravity is a force that acts between all masses. It's an attractive force. And that since the equation is gmm over r squared, the bigger the masses are, the more gravity there is. And since it's divided by r squared, the farther apart they are, the weaker the force is. Okay? Okay, so let's practice this a little bit. Remember, F equals gmm over r squared. So we'll put that up here. F equals gmm over r squared. So imagine we have the Earth and the Moon here. The Earth has a certain mass, the Moon has a certain mass, we're a certain distance apart, and there's a certain amount of gravity attracting them to one another. If I was to double the mass of the Moon, what would happen to the force of gravity between them? How much stronger? Double. Great. So that would be 2F. that make sense? What about if I doubled the mass of the Earth and kept the moon the same size? Same thing, 2F. Okay? What if I doubled the Earth and I doubled the moon? It would be how much? Oh, it'd just be F? You double one MA and you double MB and those cancel each other out? Oh, no. 4 times bigger. 4 times bigger. Now, notice that these numbers are being multiplied, so let's think about that for a second. What if I double one and triple the other? What do I get? 6 times. It's not 5. We're not adding them. We don't get 5 times. So double one, triple one, you get 6. Triple both of them, what do you get? 9 times. It's a multiplicative thing. Cool. Now, let's go back here and say that, oh, there's a force F between them. What if I was to double the distance between them? What happens to the force? It's twice as weak, but don't forget that. It'd be 1/4 as strong or 4 times weaker. Okay? Good. What if I cut the distance in half? 4 times stronger. That's exactly the same as doubling both masses. You could do either. Okay? What if I double both masses and I double the distance? Double both masses and double the distance. All right, good. It's the same. You're absolutely right. You were absolutely right. I didn't say anything. So Newton's law of universal gravitation does a lot of things for us. First of all, it explains Galileo's discovery that all objects fall with the same constant acceleration. The law of falling bodies can now be explained. It also explains Kepler's third law, and Kepler's second law for that matter. Kepler's second law basically told us that planets move faster when they're close to the sun and slower when they're farther. So how does Newton's law just explain that for us? So let's see how Newton's law of universal gravitation explains the law of falling bodies that says that all objects, regardless of mass, will fall at the same constant acceleration in a vacuum. First, we'll start with Newton's second law, which tells us that F equals ma, right? F equals ma. And when we're talking about falling objects, what's exerting that force? Gravity. Gravity between what and what? The Earth and the object. We're assuming we're on Earth doing this. So now I know that I can take this F and make it become G, mass of the Earth, mass of the object over r squared. And that should equal the mass of the object times the acceleration of the object. Does that make sense? F equals ma? Right? Now I can just do a little algebra and say, oh, I got mass of the object over here and mass of the object over there. And notice that the acceleration of a falling object is determined by big G, which is a constant, the mass of the Earth, which is a constant, and the radius of the Earth. It's not determined by the mass of the falling object. Regardless of the mass of the falling object, they'll all have the same acceleration, assuming that they're falling towards the Earth from the same height, relatively. Does that make sense? Okay, now here's something that IB definitely wants you to make the connection of, and I want you to see how Kepler's law gets explained. You don't have to know specifically how this applies to Kepler's law, but this relationship is something you'll need to deal with regularly. Notice that planets orbit the sun roughly in circular motion. Kepler told us they're not circles, they're ellipses, but we'll say it's close to circular motion. What is it that's exerting that centripetal force on the planets? What? Gravity. So there is a centripetal force because planets are going in circles, and the thing that's doing that centripetal force is gravity. Whenever you have something that's going in a circle and gravity is doing it, you can set those two things equal to each other. So I can say that gravity, G, mass of the sun, mass of the planet over the radius of the planet's orbit squared, there's gravity between the sun and the planet, right? I can set that equal to centripetal force because that is what's exerting the centripetal force. So I can say mass of the planet, 4 pi squared r over t squared. Does that make sense? Yes. So that recognition is something that you need to be aware of. When things are going in a circular motion, and if gravity is doing it, you can set gravity equal to the centripetal force. Okay? I'm going to do some rearranging here, and watch what happens. T squared over r cubed equals, mass of the planet goes away, and I'm going to have 4 pi squared over g mass of the sun. Now, I told you that with Kepler's third law, that he said if you take the period squared of a planet divided by its radius cubed, you get a number that is the same for all the planets. Is constant, and the mass of the sun is constant, and 4 is constant, and pi is constant. So that is the value that you get, regardless of whichever planet you're talking about. Okay? Mass of the sun. Here's an IB question. See how you do. Multiple choice. Should be pretty easy. You got a 25% chance at worst. And this, Arnold, gets to, I think, what you were asking about a little bit. So let's talk about this for a second. The answer is C. The answer is C. When I introduced gravitation and I said where the r squared in the equation, where do you measure that r from? The center. So if we're talking about giant planets, it doesn't even have to be giant planets. It can be anything. What you can assume, and this assumption actually, there's a mathematical explanation behind it, and Newton assumed this as well. You can assume that all of the mass of this object is concentrated at its center. And it's as if the mass were a point, or what's known as a point mass. So we'll talk about point masses a lot. Even though things aren't point masses, we treat them as if they are when we're doing calculations. Okay? All right. That's a good one. IB question number 2. See if you can figure this one out. Treat them as if they were point masses is because they're so far away relative to their sizes that it's as if they were points. All right? The radius of the Earth compared to the distance to the sun is way smaller. Okay. C is the correct answer there. Last thing. The last thing to finish up this whole puzzle is to figure out what the value of big G is. Big G is known as the universal gravitational constant, and it was first measured by this guy, Henry Cavendish. And this is well after Newton's time. Newton recognized the relationships, but he didn't know he couldn't do the calculations because we didn't have a measurement of big G. The way Cavendish did it is pretty ingenious. Here's what he did. He took a cable, and from that cable he hung a bar with 2 masses on the ends of it. And he brought 2 larger masses close to the smaller masses and recognized that those masses would have an attraction gravitationally to one another. And that attraction would cause the cable to twist. And the cable was set up so it was kind of like spring-loaded, so that it would twist a little bit and then kind of bounce back. And he knew how much force it took to twist it. So by measuring the mass of the objects and how far apart they were and how much it caused the cable to twist, he was able to get how much gravitational force there was. He had all the variables in the equation, and he could solve for big G. So then, once he did this, he got his measurements, and he came up with a value for big G of 6.67 times 10 to the negative 11th. Yes. The units on this are such that when you plug it into the equation, F equals gmm over r squared, if your masses are measured in kilograms and your radius is measured in meters, this unit of big G will cancel out so that you'll be left with newtons. Right? So the kilograms and the meters will cancel out, and you'll be left with newtons. Okay? The reason it says weighing the Earth is because now, when Cavendish measured a value for big G, he effectively weighed the Earth, because now we had a way to solve for the mass of the Earth using gravity. Other than that, how do you figure out the mass of the Earth? You don't just go out in space with a bathroom scale and say, hey, climb aboard. You can't do that. But once you know the value of big G, you can use Newton's equation to solve for the mass of the Earth. And that's what they did. And you just basically do it this way, which we don't have to do right now. No. Just know that it can be done. All right. So I want you to calculate the force of gravitational attraction between the sun and the Earth. Here are some constants, some values that will help you. Once you've done that, please tell me how does that compare to the magnitude of the force of the Earth and the sun, and why does the Earth go around the sun rather than the sun going around the Earth? Okay, so there's your answers, 3.56 times 10 to the 22nd newtons, which, by the way, you guys, that's about 8 times 10 to the 21st pounds of force, which 8 times 10 to the 21st is 1,000, let me think about this for a second, 1,000 billion pounds of force. 1,000 billion pounds of force of pull between the sun and the earth. Does everybody understand that the earth pulls on the sun equally to the sun pulling on the, and what's your explanation for that? Why is that? Equal and opposite, so Newton's third law, that's one reason. Or, okay, and you've also got the equation, GMM over R squared. It's either mass of the sun, mass of the earth, or mass of the earth, mass of the sun. Either way, you get the same answer, right? Now, I want you to think about this for a second. Let's go back here, not there, but here. Here, 6.67 times 10 to the negative 11th. Is that a big number or a small number? Small. It's very small. And what does that tell you about the gravitational force? It's incredibly weak. But wait a minute. You just calculated that the sun's pulling on the earth with 1,000 billion pounds of force. That's not very weak. So what makes gravity strong? Mass. So gravity is terribly weak until masses are large. And then suddenly it's significant. But the reason you guys aren't sliding across the room and smacking into each other because of your gravitational attraction is because your masses are so small that the gravitational force is quite weak. Yeah? It is the weakest force of them all. Not even close. Electromagnetism, weak nuclear, strong nuclear are all much, much, much stronger than gravity. What's that? If things get really close, they can be pretty strong, but even like if we get down to an atomic level with like protons and electrons, they're really close, but their masses are so small that gravity is pretty negligible. The mass really, proximity can affect it, certain. Okay, let's look at another quick question. What if I turned off the gravity between the moon and the earth? You know, the moon and the earth are attracted gravitationally, that's why the moon's in orbit. If I shut off the switch and turned off the gravity, and instead of gravity, I had a steel cable hanging onto the moon, making it go around the earth, how thick would my cable have to be to exert the same amount of force as the gravity between us? And here's your choices. You've got a bass guitar string, you've got a cable that holds up the George Washington Bridge or like the Golden Gate Bridge. You've got one of the World Trade Center towers, which isn't there anymore, but like a really big skyscraper big around, or as big around as like Manhattan, or as big around as like the whole state of New York. Talk to your, okay. So there's our, what did you say, Arnold? What do you think? E. Arnold thinks E. And the correct and for true answer is actually bigger than E. It's actually bigger than E. So what we've covered today, you guys, is basically introducing you to Newton's law of gravitation. We'll have to talk more about field strength. We haven't gotten into that yet, okay? We've talked about this equation quite a bit, I think. So then we just have to deal with these two, and we'll be good. You can do one for the group.